Ko whoratū waka no whangarahau, ko Paul Gardner tāku ingoa. Kia ora folks, thanks for that lovely introduction. So my name is Paul, based at the University of Otago in the biochemistry department. Thank you. That'll become important later. It's been a long day, man. All right. So my group works on a fairly diverse range of problems. So we're interested in genome annotation, developing bioinformatics tools, applying bioinformatic tools, working with different sort of machine learning approaches, working out what's a gene, what's not a gene, that sort of stuff. It's all quite fun. Analysing genome variation, which we were chatting about before. And then one of the other things we do is try to work out what's a good software tool for the sorts of problems we're trying to solve. Now, it turns out bioinformaticians are horrible people. They don't like using other people's software. So we will often go, oh, we could do that better. And you try to hack together a bit of code, get something working, push that out and inflict that on the rest of the community. Which then means you can often have, 5, 10, even up to 100 different tools that all claim to solve pretty much exactly the same problem, which then leads to a big challenge, right? So how do we choose a good software tool? So when you sort of survey people, researchers, they'll often come back with, well, the developer worked down the corridor from me, I know them, they're great to have a beer with, so, I'm going to use their software tool. They might be quite famous as well, so lots of citations, quite senior as well. The tool was published in a really good journal, so therefore we're going to use that. Nature Methods, for example, there. Other people will just choose the most recently published tool there. So it was in bioinformatics last week, therefore that must be the best one there. Others will be, well, everyone else in the community uses that tool, therefore I'm going to use that one as well. Some people will go, well, the tool was really fast. I didn't have to wait long for a solution. Or conversely, I had to wait a week for the solution for the prediction to come out. Therefore, it must be a really good tool because I burnt a ton of compute getting the solution. So in my group, we usually just try to run the tool on some test data, and is it producing reasonable results or not? So find some positive controls, generate some negative controls, run the tool. Can it distinguish between those two groups reasonably well? Now, if you're getting bored during my talk, I've provided some pictures of my office throughout as well. Hopefully that will keep you awake. This is my northern office up near Taranaki there. So we've published a few studies in this space. So I started out looking at RNA secondary structure prediction tools, moved on to multiple sequence alignment and homology search. We've looked at metagenomic tools, RNA-RNA interaction tools, and we're just trying to get this study published at the moment, where we're looking at protein coding, annotation, and nucleotide sequences there. So that's still a work in progress. So we've published a few of these, and one of the things I noticed after publishing a few of these is that every time I ran one of these benchmarks, pretty much, there was some tool that took like a week or a month to run and was not very accurate in terms of the results there. So this graph shows the speed. So if you want to be very fast, you're over in this corner. If you're very slow, you're over on this side of the graph. And that's versus accuracy on the y-axis there. So if you're very inaccurate, no better than a random number generator, you're down the bottom there. And if you're super accurate, completely separate, say, your positive and negative sets, then you're right up the top there. Now, most of the bioinformatic textbooks will tell you if you want an accurate, sort of mathematically complete solution to a problem, you've got to burn a lot of compute to do that. Okay, so accurate tools are slow. If you want speed, you're going to have to sacrifice accuracy to get a fast tool. Right? So theory should state that most bioinformatic tools should sort of lie in this band here somewhere. Right? So technically, these shouldn't really exist. Right? We shouldn't really have slow and inaccurate tools. I mean, conversely, we shouldn't really have fast and accurate methods either. But we definitely have sort of outliers. And that was pretty consistent across every study that I ran. So I got a bit curious. I thought, well, this could be a thread worth pulling. Let's dig into this a bit more. It's kind of a silly question, really, but we'll crack on and have a go at it. At that time, I had a few grad students, so we sat down, trawled the literature. I wrote some dodgy code myself because I didn't want to use anyone else's. This is before the days of large language models, and so I could rank sort of PubMed articles on how well they match my search criteria. And so we found around 70 different benchmark articles, and they cover more than 500 different bioinformatic tools. And so I could extract from those articles relative ranks and accuracies in terms of, relative ranks of accuracy and speed for each tool. Does that make sense? Yep. Groovy. Then at the same time, while I was at it, I gathered statistics on each author. How well cited are they? The impact factor of the journal. How well cited is the tool? How much GitHub activity was there for the project where the tool was available from? What else can I say about this? There were different sort of accuracy measures there, so that was a potential issue, and these cover a range of different bioinformatic problems as well. Right, so results. What am I showing here? So I like a good permutation test there. So basically for each tool or for each benchmark, I shuffled all the ranks as well, did that about 1,000 times for everything. That gives me sort of a background sort of ranking for each tool and for each, quadrant is the wrong word. What's a 3 by 3? There. Well, whatever a ninth of a nonad, thank you. Nonad. Yeah, that'll do. So in this 3 by 3 grid, we've got speed along the bottom here, accuracy along the top. If you're really good, you're up in this quarter. If you're slow and inaccurate, you're down in there. So the significant results were in this nonad. Here we had an excess of tools, right? And this is in brown here, the distribution for the random rankings there. And so that was a pretty major outlier. This is the real data point up there. But that was not nearly as significant as the gaping hole in the middle of the nonad there. So what that says is in bioinformatic sort of software space, we have almost no tools that are sort of middling in terms of speed and middling in terms of accuracy, which is kind of weird. I think this might be a form of publication bias. So if you're the first cab off the rank, you can be as crap as you like in terms of software space. You've got to get that published. Everyone who publishes after you has to show that they're either faster or more accurate. And good luck trying to get published if you're neither of those there. And that may explain this whole, I don't know how to test that idea though. So the next obvious question was, well, if it's not speed, what does drive accuracy for software? So is it sort of reputation-based measures or something else going on there? So I measured how old the tools are, the impact factor of the journal, so H5s there, H indices of the authors, citations for each tool, and then some of these GitHub based measures there. And so we've sort of got reputation and GitHub activity sort of all sort of cluster. This is a covariation matrix up there, and then sort of AG type measures down there. Then again with a sort of permutation based test, we can see what's the difference between the real sort of accuracy based ranks there and what's the relationship, correlation between randomized data and the real observed data there with accuracy, okay? So, H-index and journal impact factors basically do exactly what a random variable would probably do there. So near zero correlation with accuracy there. So you can pretty much ignore authors based on this, or at least H-indices of authors there. How old the tool was, how fast the tool was, and how well cited it was as well, so how widely used it was. Also, not a useful measure of accuracy there. And then finally, activity on GitHub and versioning of the software were pretty significant predictors of accuracy there. So that's kind of useful, right? It indicates that sustained development of the software meant the software is generally quite accurate and therefore good there. So that was a good takeaway. And most of the things we spend a lot of time worrying about, we probably shouldn't be worrying about as academics. Right. I'm not going to beat Mick in his 12-minute talk this morning. All right, so very briefly, we ran another study as well. So this was looking at that coding stuff. I gave a talk at a conference about this not so long ago as well. It was a genetics conference, so as a joke, so this is sort of how accurate the tool is along here. And then as a bit of a joke, I sort of added the department labels onto the graph as well. And then I could tell the geneticists that they were pretty crap at writing software. In fact, one tool out of a genetics department was only slightly better than a random number generator there, which was kind of fun. You mentioned 30-year-old software. This tool is 50 years old over there and is outperforming some very fancy neural network based methods and support vector machines as well, which also amuses me greatly. So I thought it'd be interesting to dig into the department side of things a little more as well. There were some other issues going on that sort of led me to this. So I could take the same accuracy ranking data, map each of the tools onto the department of the corresponding author as well. And so for the 500 different tools that we looked at, there are around 100 that map to a genetics department, 100 or so that map to a bioinformatics department, 80 to 90 computer science-based departments, and then the other 300 or so were sort of split across other research fields there. Is that all clear with me so far? Cool, so that was kind of fun. There, I also pre-registered the study as well, so I documented the methods I was going to use and some of the expected outcomes and things like that, which meant I couldn't hide the results either, which will become important in a second. So this is, in pairwise comparisons, how often did each department win? So pleasingly, medical informatics won more times on average. So if your department happened to be medical informatics and you're producing a software tool, your tool tends to be more accurate on average. Bad news, if you happen to be in a biochemistry department or a bioinformatics department writing bioinformatics software, your tools tended to lose more frequently compared to other departments. So we're generally lower ranked in terms of accuracy. Mick likes a good confidence interval, so I use bootstrapping to add those. I could use that to compute Z-scores. I could use those to compute p-values. somewhat fortunately, so I did all that. So medical informatics won sort of 70% of the time on average, Z-score of 1.88. P-value after correcting for multiple testing was only 0.29. Okay, so that was sort of the most significant department in terms of accuracy there, which pretty much means nothing in the study was significant. There is no strong association between accuracy and what department you came from there, which was very lucky for the bioinformaticians and the biochemists as well, so the p-values were all quite insignificant there. So the only thing that seems to matter is a long-term commitment to maintaining good software, is kind of the punchline from this. So those studies have been published. If you want to have a look at them, you can grab them off my Google Scholar or elsewhere. This is my most recent office down in Lake Monowai. It's quite nice. And thanks to the various funders there, and thanks to you guys for listening.
Thanks, Paul, for the interesting scientific way to present the bioinformatics tools accuracy versus the speed. Any questions and comments for Paul?
Yep.
It looked like number of issues was the most positive one, but then there was, but on the other side was unresolved issues, which was a poor predictor. Is that just kind of measure of community engagement?
No, it was still correlated, just a negative correlation.
Yeah. So if you've got open issues.
Obviously lots of users, people submitting issues, if you're actually engaging in that.
Contributors commit like just kind of engagement. So it seems like it's not how good you are at that. I mean, what's your perspective on this, on terms of if you're writing software, what should you do to get engagement? Is that the kind of takeaway, or should you?
I haven't really dug into that specifically, but it would be definitely an interesting thing to follow up on. But yeah, it does seem like building a good community who are providing feedback on your code and you actually addressing that feedback is not a bad thing, at least. You know, I'd be a little cautious about over-interpreting like the relative rankings for each of these different sort of GitHub-based metrics, because there is sort of multiple testing and things like that going on.
Yeah, but those are all related, right? The commits, pull request, forks, it's all, people might be doing all of them.
So I'm not showing p-values for any of these. So just the circled ones are, less than 0.05 after correction.
Oh, cool.
Yeah. But yeah, good question. It's probably worth following that up.
I've got to follow up on this notion of sustained software with a little story about a person who did make a request to install some software because it was the newest and greatest thing that they had seen. And after we went through the process of installing it and what have you, we realised that it was grep and a word count. And of course, that piece of software got abandoned very shortly afterwards. The person put it together and went, oh, okay, that's a bit of fun. Of course, grep's been around, early 1970s, originally from ED.
Highly optimised.
And still is in continuous development. And that's, it just I wonder how many of these tools actually really just sort of are more elaborate and fragile versions of what could be sort of like a sequence, a pipe of sort of like existing well-established command line tools that are still in active development since 1970.
Any other questions?